Hi, everybody. I'm Steve Napier from Bodawood. Welcome back to those of you who have joined us before, and my colleague Joe Ballister,
Hello.
and a wonderful presenter who's currently in New Zealand, Jason Quinn. Hi, Jason.
How are you guys doing?
Thanks for joining us, Jason.
So, just a little bit of background. We'll just wait while people are still joining. A little bit of background. So, Jason is um, I think you were the only certified passive house certifier in New Zealand.
That's correct. I'm the only passive house certifier in New Zealand.
Fantastic. And you've worked on a few projects here as well.
Yeah, we're certifying some projects in Perth and Sydney.
And you were actually just asking before about, and this, if people could just maybe put it on the right, because I couldn't actually find somewhere to put a poll or anything, but Jason's just interested to know, and we are as well, what made you come to join the Passive House webinar today? And just a little bit about your interest in Passive House. So you can put it in the public chat, or you can just maybe send us a private message, just a couple of words as to why you're joining us today and your interest in Passive House. Really love to know.
Now, Steve, we're covering some CPD questions at the end, aren't we?
Yes, we will. So for everybody, the handout for the CPD questions, if you struggle to get it, you can get it in our handouts on the right. Some people have struggled to save it and that kind of thing. More than happy for you to just copy the questions and then put them into the body of the email and just send it through. So for those of you who are wanting formal CPD points, and I'm just sending you my email address as well. Just send them to me and I'll get your certificates to you within 7 days. Yeah, loving these. Interest in passive house in tropical areas, interested in sustainable solutions for housing, doing a low energy house. Fantastic.
So
this is awesome.
In the chat, we'll deal with them at the end, as well as the CPD related questions.
Oh, thanks, Catherine. Now we're going to just want to tell you a little bit about us as a company, about Bodawood. So Joe and I are based here in Oz. We work directly for the company, but our distributors here on the East Coast is Britain Timbers. And then on the West Coast in Perth, it is OzTim. And that you can actually grab their details on the website. But just a little bit about us. So basically, we source sustainable timber from the kangaroo forest in the North Island of New Zealand. So it's all FSC timber. And basically, we do what we call thermal modification. So using a very, very high heat to treat the timber. And then that gives us the ability to, well, basically what the high heat does, it increases our durability, but also makes the timber very, very stable as well. You look like you wanted to say something, Joe. No. So we do very large sections. So we do light structural. This is our cabin near Queenstown in New Zealand. So we can do very large sections, also for posts and pergolas, that kind of thing. Can we curve? Are you referring to cladding, or what type of thing are you thinking, Camilla? So yeah, I mean, back to sustainability. I don't know, but I'm absolutely going to ask the question because that's really good.
If there's a project, I guess if we've got a project to work on, we can do some some product development around curving.
And we can also it gives us an ability to do very large spans. So I actually measured the drawings on this one and found that the longest span was 3.5 meters. And I asked someone who'd been there recently, and I believe that this was still looking like it had been put up the day before, like it was looking really, really good.
Facade blades and screens. So if you have an application like that, let us know, and we will continue to do some development work on that front.
Yeah. So I mean, yeah, basically you can do things that you can't do with hardwoods and so on. And then we also have the ability to do very dark colors as well. So black is a very big thing right now. So even, on very wide boards, if you wanted to do like a 175 cover type thing, we can do that in black.
And the reason we can do that, of course, is because the timber is so stable, as you say, Steve, and it can handle the heat, and it won't move around so much, so that the integrity of the coatings stay together. And also our unique finish or coating, roughened bandsawn finish on the timber allows more penetration of the coating to keep the blackness, if you like.
Cool. Yep. We should get going. Numbers have kind of stabled out, but I'll hand this over to you. I can see you've jumped. Let me just put back your slides, Jason.
Thank you. Appreciate that. Good preview of what we'll get to see today. So we'll go through a lot of things.
There's a lot to cover today. Yep.
There is, but we'll take it at a reasonable pace, so it shouldn't be too bad. And I'll try to, and we'll try to finish it at 45 minutes after the hour. Yeah, it's a different time zone for me.
We're
So go ahead.
We're going to drop our faces off, and then we'll see you guys at the end. And yeah, that way you can concentrate on this.
Yep, and also it means I can drink tea while we're talking.
Absolutely.
Yeah, so just a little bit about myself. So I shifted to New Zealand about 10 years ago. Before that, I was a rocket scientist. I worked at NASA for about a little over a decade doing systems engineering. So when I shifted to New Zealand, I wanted to try something different and see how I could make a difference in the world, and ended up growing into Passive House, as it were. So I've been doing Passive House for about 8 years now, and started off with, like most people who get into Passive House, with doing 1 or 2 homes, and then moving into more and more projects, and then finally becoming a certifier. So I'm accredited certifier with Passive House Institute in Darmstadt. And as well, so I run a small consulting firm with 4 of the technical staff here in New Zealand. And we design and certify projects throughout New Zealand. And we also certify and help with some more advanced consulting on projects in Australia as well. So we do quite a bit. So we do some more advanced training and that kind of thing. So I think I've got control of the slides now. So let's jump to the next one. So what is a Passive House? And this is a Passive House project in Exeter, which is in the UK. And they've done an immense amount of social housing. So this is my favorite definition of Passive House. In Passive Houses, people can live in homes that are comfortable and affordable to heat and cool, homes that are low carbon, and homes that help us all thrive, mainly through their health impacts, right? If you want to think of a slightly more interesting way to think about Passive House, you can think about, when we think about a vision for what housing should be, if you talk to architects, talk to designers, you talk to people who live in homes, like what should a home be? And what should we do forward going homes? You know, when you think about homes right now in New Zealand and in Australia, unfortunately, both have a relatively high case of excess winter mortality, where people are dying potentially because of the conditions in their homes. And we have cold, damp homes in both countries because the people in our politics have failed to prioritize health and housing property, and housing policy rather. You know, we can design buildings that heal us and help us to do our best in the world. We can design buildings where the air inside the house is healthier than the air outside, certainly in cities. You know, it's always fresh and dry in the house. We can design houses where you don't have kids going to hospital with housing-related disease. This still happens quite a bit in New Zealand and in Australia. Australia actually has more mold than New Zealand does. A house where the house just keeps itself dry. The towels dry themselves in the bathroom. You don't have a towel reel that you have to turn energy on into to dry the towels. A home where, you know, we can build right for the long term. you know, the leaders in the building industry today, they build houses to the lowest legal standard. I mean, any worse than it would be illegal for them to build those houses. But instead of that, we can have buildings where they're a gift to people that come after us in society. You know, we can build buildings where they're built for the long term, so they're low carbon. They've got less steel and concrete, more timber. We build homes where there's no fuel poverty. When I talk about passive house with clients, oftentimes they're older. They've gone through a few houses. They've built a brand new code house and they realize it's still cold and damp. So they want to build a passive house now. And they're like, I should have done this 15 years ago. I would have saved all that energy. I would have had all this better environment all that time. And it's sort of like that whole adage you hear about a tree, you know, the best time to plant a tree is 10 years ago. The second best time is now. So for many of our clients, at least, the best time for them to build a passive house is now because they couldn't do it 10 years ago before they heard about it. So this is another social housing project in Exeter Council in the UK, and it's the last one from the UK. So we won't have a lot of pictures from there. I've got more pictures from Australia. So in Exeter City Council, there's one woman who led the charge towards passive house, and she did it not because she's an architect or a designer or even a builder. She's actually a property developer, and she grew up with her extended relatives experiencing fuel poverty. They couldn't heat their homes in the winter because they didn't have enough money. And so their vision for passive house in Exeter Council isn't about all the technology stuff that I love and all the math I love to do and thermal modeling. What their challenge is they're going to eradicate fuel poverty in their council area by using passive house. So all their social housing projects now are passive house certified actually. So their thing is they're aiming at that triple bottom line where they've got low energy buildings that are healthy and comfortable and that are climate resilient. So that's their vision for what passive house can be. Now, here's an example of a passive house in Australia. So this is a CLT and timber cladding passive house extension designed by Betty and Coote Architects. So this has just been certified, I think, just 2 or 3 weeks ago. So you can see this building is not only going to have incredibly low operational energy because it's got very good insulation and doesn't need much energy for cooling and heating, but it also has a very low embodied energy in the materials of the structure because it's all cross-laminated timber structure. And then, of course, it's got timber cladding. I wish we still had our faces on so I could make fun of the Bodo guys. I don't think this is a Bodo here. They should have done a better job of selling, I suppose.
I don't know if I got onto that one, but I did speak to Knut about that one, so I will definitely follow him up.
You should definitely razz him a bit, see why you didn't get into that project. So, because they've got a little bit of background on building biology, I believe, so they'd be interested in non-chemical.
Yes. Yeah. Anyway, sorry to keep going.
No, it's good for you to jump in. I actually prefer it. It's a bit odd sometimes speaking to a camera. So, and this is another certified passive house. This is the first non-residential passive house it was the first non-residential passive house in Australia. So it's a child care center. So it's built and certified. And this is built with a panelized system. I'll show you what a timber panelized system. So this is all timber frame. It's got brick cladding on a few walls. So it's all prefabricated timber panels that are then dropped on site onto a concrete slab that's very well insulated. And this has been certified as well. You can see who the architectural designers are here. And the passive house designer was Harley. So quite a beautiful building. And very, it's interesting because when you look at German passive houses, they don't have a lot of glass, but this building's got glass everywhere. So here's another passive house. This 26-story tall building here is a passive house dormitory in New York City. So this is a very, very large passive house. At one point, it was the largest passive house in the world. And I think about 6 months later, it got passed up by a couple meter tall building in Spain, actually, called Balboa. So you can see passive houses aren't just homes. They're also very large buildings. Here's another passive house. This one's under construction. It's nearly done. This is a structurally insulated panel building with 17 units. So this is a co-housing building. So all these buildings will be certified. Well, I'm hoping they'll be certified. I'm the certifier. They've passed a design stage review, but so I'm hoping they'll pass a final review and that'll be certified as well. And projects in Australia have been bigger than the ones in New Zealand. This project in New Zealand will be the largest one in New Zealand when it's finished. So let's just talk for a minute. I don't want to talk about numbers very much in this presentation because it's an introductory one. But it's important that you realize that passive house standard is both a standard as well as a process, if you want to think about it that way. So the standard is this idea that you have to hit a heating and cooling metric, a level you can't go above or you fail. And then you have some building quality metrics, and then you have a social justice metric. It's really quite obvious when you look at the numbers. So the heating and cooling demand metric is this 15 kilowatt hours per square meter per annum for both heating and cooling. That's the total energy you can use per square meter of the building. So that's a very small amount of energy. That's on the order of 10% for a typical building throughout most of New Zealand and Australia for heating and cooling, and a peak load less than 10 watts per square meter. Now, this heating and cooling load metric assumes you condition a building all the time. In other words, you're not letting the building get to 10 centigrade in the winter and 35 centigrade in the summer. This is assuming you condition the space. And then they've got these build quality metrics you have to hit to meet the pass-fail standard. So there's an air tightness standard of 0.6 air changes per hour at 50 Pascal. You could argue what the numbers are, and it is much tighter than what it currently is in Australia. But the real key is you can't unintentionally hit that target, even with a structural insulated panel building, which has got big continuous panels that don't leak air. You still need to pay attention to the joints to hit that target. So it's sort of a build quality metric more than it's anything else. You have to also not have moldy junctions. And they check for that. And also in the summer, you need to check that the overheating limit's met. In other words, the building doesn't overheat more than a certain amount of time and a certain temperature level. And then finally, there's a social justice metric, which is this primary energy renewable, which is the idea that you have the whole building for all uses in the building, including appliances and plug loads and such, which are estimated. It has to stay below a certain limit, and that's and that primary energy renewable limit is a function of how much renewable energy we can generate in a country. Looking forward to a fully renewable grid. So there's just to think about the pass-fail standard. There's just these three kind of categories of metrics you need to meet: overall heating and cooling metric, which is just the heating and cooling energy; a build quality metric; and then a social justice metric. And then the process you do that is typically when you're designing pass-fails, you have a conceptual design level and design development schedule, just like you do for when you're doing normal design about building. But the initial thing is you build an energy model or a thermal model of the building very early on in the process, and you try to follow through the design process of that thermal model. And if you're going to certify the building, you have a third party, a certifier like myself, or there's other certifiers in Australia. There's 2 others. And they would go through and make sure your model's correct. They'd check all the entries to make sure that it's going to be certified. And that's what the certification process entails. In Europe, they've been doing pass-fails for a lot longer, and they still have a thing we'll talk about in a minute called performance gap right here. So this bar graph here on the left is for buildings in the UK. And this is actually measured energy for heating. And you can see that the average, basically the different color reds and the different color of the green and red here and where it says passive houses are from predicted versus actual measured. And the variation was quite large. And in all cases, the measured heating energy was much higher than the predicted for the non-passive houses. Whereas for the passive houses, the prediction and the measurement were very, very close. Now, that's not only due to the software they use to do this calculation with, which is quite good, but you can use any software. It's like a carpenter. You can use any hammer. It's just some are better than others. And so with this tool, the certification process checks the entries to make sure they're correct. And because of that, they don't end up with a performance gap. You end up with what you predict before you build the building matches what the building actually experiences in terms of heating energy. So because you can really accurately predict the results, it means you can design the building to hit that result. So instead of designing a building and saying, well, this is a good low energy building and it's going to be pretty good space in here, you can actually say, no, it's going to be X amount of heat per year is what's going to keep the space at 20C. And you can know that when you say X, it's X plus or minus 5% or 10%. It's very accurate. And that's when you measure it under standard conditions. And then they've done this across many buildings and done full sweeps across different certified buildings at different levels and show that the averages match very, very accurately to the prediction. All right. I showed you passive house in different buildings. We showed you single family homes and a very large 26-story residential dormitory hall and a school, and they're now doing passive house hospitals. You can also do passive house retrofit projects. We have an existing building and you do what they call an enter fit, that's how you say it. And it's a retrofit project where you take an existing old building and you go stepwise along the way to fixing it. So I had a client call me a few weeks ago. She's now working with us. And she's got an old building in Wellington in New Zealand, which is cold and windy, if you don't know that, in the winter. And she wants to know, she's going to replace all her windows. But she eventually wants to have a low energy building. She wants to have a passive house eventually someday. But this year, she's going to replace all the windows. So she wants to make sure that the windows she put in are not going to make it so that she can't ever get to that level. So that's what this enter fit is basically you start with the end in mind. So you start with, at the end, I want to have this house that's very high performance and has very low embodied carbon. And so to get there, I'm going to do these steps. So when I put the windows in, I'll make sure the windows are installed so that I can move them into the insulation layer later when I eventually insulate the walls. I'm going to make sure when I redo the roof, I insulate the roof well enough, not just to capture the first cost savings, but also the roof's well enough insulated that when I do the walls and windows, it all works together. So the idea with Enerfit, the Passive House retrofit plan, is you develop this whole plan, just kind of sketch it out, and then you can do the first few steps and get pre-certified. So it might take you 40 or 50 years to retrofit a building because you're not going to replace the roof until the roof wears out. But you can begin with the end in mind, avoid locking in poor performance later by making a good plan. All right, so Passive House focuses on the architecture. That's, in my opinion, that's why they should call it Passive House. I think everybody would think a different name might be better. This is a certified Passive House in the South Island of New Zealand. Very simple form. This building, they focused on the envelope of the building, fabric. So they didn't add fancy mechanical systems and PV everywhere and all that stuff. There's some PV on the garage next door. But this building, they focused on a simple envelope. They focused on the passive element of that building. There's a heat pump in here. The heat pump will be replaced in 15 or 20 or 40 years, but the envelope of this building, it potentially will last 100 years. It's all timber and fiberglass insulation. There's no reason it should wear out. That particular building, this is panelized construction. The school that I showed you in ACT was built exactly the same way. Prefabricated timber panels with, in this case, fiberglass insulation and a IntelliMembrane on the inside. They were all then brought on site, trained on site, and put together, and you stand the building up quite quickly. And then you seal up the IntelliLayer on the inside for air control. So panelized construction is happening both in New Zealand and in Australia. The paneling system used in that school in ACT was by Carbon Light, L-I-T-E. You can look up their panelized system there. They're quite a good company there. Passive House is performance-based. There's lots of fabric options. You can do pretty much whatever you want as long as it meets the performance targets. It's not prescriptive. So this one shows you a structural insulated panel building on a timber floor with fiberglass on piles. And this one shows you an insulated concrete form building, which is not my favorite building in some ways, but it is very, very durable. So this is a brilliant building if you've got an area that floods, for example. You can open the doors up and let it flood through the building, and then you basically just hose the whole building out when you're done. You think that's kind of funny, but there's actually a Passive House in my hometown of Wanganui here that's built this way. It's right on the river, and it floods every 2 years. So it's a yoga studio. They've got an exposed concrete floor. They just wash it out every 2 years. And they're back teaching yoga classes 2 days later. This is a most common construction method used in New Zealand, which is a timber, truss roof, normal timber walls with another layer of insulation and an air control layer. This one's showing a plywood air control layer and a concrete slab that's very well insulated. And we'll see more of this later. This is a love-hate chart for me. So when you talk about Passive House in a common sense, most people will talk about the Passive House fundamentals. And, so I'm sorry, the company that does panelized constructions in Australia is Carbon Light, L-I, so C-A-R-B-O-N.
Yeah, I found the link. Thank you.
Good, thank you. So, so I hate this slide and love it at the same time. Obviously, I put it in my presentation. I chose to. So these are 5 things that you typically find in passive houses in a lot of places, in cold climates and also in hot climates. But if you're a good passive house designer, you can break every one of these rules, just not all at the same time, as it were. So you can have a passive house with some thermal bridges. You just need to manage them and offset make sure there's no mold risk, and then offset that. You have to have air tightness in a passive house, but you can bend that rule and use a low energy building perhaps. Most passive houses have mechanical ventilation with heat recovery, but there are some passive houses that don't use heat recovery. They just use balanced ventilation. Typically passive houses have triple pane windows in very cold climates, but certainly in Sydney and North, I would expect double glazing unless they've got a building that's really, really small or oddly shaped. And most passive houses have thermal insulation, but that level will vary significantly depending on where you're located. And I've shown that with an example building. So this is the Abodo cabin, which is in Wanaka in New Zealand. So this is a display building as well as I believe it's a beautiful snow cabin. So I think the photo showed earlier with this. So we're going to talk about this cabin. As you can see, this building, it's a very simple shape, and it's got some glazing behind that wood facade. So this is what it looks like both on the inside and the left, and on the right, it shows you the outside of the building. So when we look at this building, I've got a cross section in the middle to kind of talk through the construction. It's an interesting setup. So this building was optimized to display the timber, obviously, right? So the inside, you can see on the left here, you can see all the timbers displayed, and the rafters are displayed, and the beautiful treated floor which Adobe made. And I think they also did the wood in the countertops as well. Yeah, they did actually. So this building was designed to display the timber, but they wanted to have good insulation. So what they've done is they basically put a warm roof around both the roof and the walls of the building. And in doing so, they made the walls and roof about an R5 assembly. We use metric units in New Zealand and Australia, so it's R5 metric, right? And then the floor is a simple timber floor, particle board floor underneath the Adobe finished timber. And then it's got a fiberglass insulation between joists, right? So simple building. And this building is built about 200 meters above Queenstown in New Zealand. So quite a cold climate. Actually, it's the coldest climate I've looked at a house in New Zealand. So that building in New Zealand in its home location uses about 98 kilowatt hours per square meter per annum. Now, remember we talked about the passive house level being 15. So that building uses considerably more than a passive house. But the interesting thing is if you actually, I also looked at what this would be if you did a minimum code New Zealand building, and that structure would be 300 to keep that building warm all winter. So it's already, even with just R5 walls and roof, it's gotten down to a third of the code allowed level. But to get down to 15, you'd have to significantly increase the insulation of that building and go to triple glazing. I forgot to mention it has Adobe timber windows with double glazing in it as
awesome.
Well. And
I said, awesome. Thanks for the plug.
No, I mean, you guys built it that way on purpose. And it's unusual that I get to take a building that's built and doesn't meet the standard and talk about it in public. So it's good that you guys are willing to show that, if you built this building today and we'd had more involvement in the project, I think it would have been built slightly differently. The construction system probably would have been identical, but it just had thicker assemblies. So if you can see in New Zealand, even in Auckland, which is our warmest climate we've looked at in this picture, it's still at 25 kilowatt hours per square meter per annum. So it doesn't meet the passive house standard even in Auckland, this building. Even with good double glazing and everything else done correctly, the insulation value is just not high enough for the size of the structure it is. Now, if you look in Australia, because of course everybody here is from Australia, so that's what they want to look at. So you can take that building from Canberra to Hobart to Melbourne to Adelaide to Perth to Sydney and then finally to Brisbane. And you can see once you start getting down to Adelaide or Adelaide or Perth, the building does meet the passive house standard with the way it's set up. Actually, you would need air conditioning in the last two climates in part of the year, the way that building's set up the way it is, because of the one bit of glass it's got on there, which is some sliding doors face north. So the nice thing about thermally modeling buildings in passive house is you can move them across climates and change the structure to see how the building's going to perform before you build it. So I wanted to not take too much time, but I did want to take a little bit of time to talk through some advice. So there's a lot of different ways to get into passive house. As a designer or an architect, you can go ahead and take the passive house consultant or designer course and learn to do your own math models in Excel and design them, or you can to thermally model the design, or you can go ahead and work with a consultant or an engineer to do that. But if you do that, it's oftentimes best if before you talk to the engineer consultant, you have an idea what the building looks like. Because engineers, we can't model a building we don't know what it looks like. We need to have a floor plan. We need to have elevations, window size. We need to know what the site shading is in order to do our jobs. So before you do that, when you're doing the conceptual design, those first pencil sketches, I wanted to pull together some advice for you so you can take that away. And the next time you're doing a building and you're going to work with a passive house designer or a consultant, you'd already have those things in your mind. And you could understand that if you do these things, they'll make it easier. And we'll need less triple glazing in Sydney, for example, which you should easily do with double glazing. So the first thing is I tend to tell a story about cargo cults. So there's this idea of a cargo cult. So it was interesting. A lot of people in New Zealand hadn't heard of this before, but what happened is during World War II, the Americans came into the South Pacific, and they would set up airstrips on different islands that really hadn't met civilization before. So they had come because they were trying to defend against the Japanese and all that stuff, right? So they would bring in airstrips, and the population living on those islands actually all of a sudden they had a huge influx of consumer goods that just kind of fell out of the sky. And with their cultures, they didn't really understand it. So one of the ways that they responded is they basically, after the Americans went away, after World War II was over, they tried to recreate that prosperity by running what they have cargo cults. And they basically would build mock airplanes and march around as if they were American soldiers in order to try to bring back the good times, as it were. And now, I don't want to pick on architects too much, But I see a lot of low energy buildings and architecture design buildings that are passive house. They're not actually not passive houses, but they're designed to be passive solar sort of architecture. And it's a complete cargo cult. They design a passive house that looks like a passive house. It has all those things I showed you earlier on that slide. It's got, they've looked at thermal bridges. They've got really good windows in. They've got good insulation, but they just totally missed the goal because they're not understanding the real core essence of the idea, which is that you model it. If you have a passive house, it's not because you've got good windows and you've got a ventilation system and you've got thermal bridge free design. That's bullshit. If you got a passive house, you're hitting the metrics, right? You've got an you've got a heating and cooling load lower than a certain number. So in order to do that, you need to model it. There's no other way to do it. So passive house is effectively, it's a standard that's built around their energy modeling tool. You can use other energy modeling tools just as well, but they're oftentimes much more complicated and more expensive to use. The passive house planning package tool is designed to be effectively the least energy model you can do to get a good result. So if I've got one takeaway for this whole time we spend together here, is that don't do cargo cult architecture, model it. If you've got any sort of client who's interested in how the building's going to be done, how the building's going to perform when it's done, then it needs to be thermally modeled. Otherwise, if you think you're doing low energy architecture, there's no way to know until you build it and you measure the energy. And then you're going to have to go ahead, and the only way you can make it better is by the next client build the same building, but do this better. By modeling it, you can go ahead and see what you need to do better before you build it. So the next thing in this building is by Hiberna architecture here in New Zealand. This is a straw bale passive house. It's actually the only, to my knowledge, it's the only straw bale passive house in the world that doesn't have a plastic air control layer. So on the inside of this building, the only thing keeping the air inside the building is a clay plaster layer, and clay render layer rather. And so that's got the air controller. So this building is obviously timber frame with straw bales on a concrete slab over foam insulation. So, and the reason I wanted to show you this particular building is form factor. So this building is compact. If you think about it, it's almost a square cube. So that means that there's less surface area for the interior floor area. And because there's less surface area, there's less surface area to lose heat. So that means that, and also to gain heat if it's hot out. So that means that the building is more efficient. It allows you to have less insulation and less performance in glazing for the same amount of energy. So that's really important when you're designing a highly efficient building, to be careful with the form factor. Also because the simpler you make the form, the less expensive it's going to be built, and you have more money available to spend on windows, for example. So this building's got triple glazed timber frame windows, for example. All right, and it's not a wealthy client. This is actually one built by the architect herself, along with her partner, who runs a construction firm called Hiberna. Right. This is a building in Wollongong. So this will be hopefully a certified passive house. This is being built as a show home as well as a granny flat next to an existing home, which is this one right here. And it's been highly optimized by the architect for solar gains without overheating. So the building sits underneath an existing pepper tree. So it's called Pepper Tree Passive House. It's got lattices, it's got screens in front of the windows, it's got overhangs, but the building does face west. And still, we had to be very careful with meeting the overheating limit with this building. So I'm the certifier, so I'm very hopeful that they'll come back to me with a built building that passes the blower door test, and I can certify it because they've passed the design stage certification review. And you can see they've got solar panels on this side here that also overhang these windows and provide shading. So it's important in passive house to put in windows for daylight and views, not for energy gain. If you have a building that doesn't have enough heat in it, you want to just add insulation, right? You don't want to, if you've got a car that's I won't use that analogy, sorry. I'll stay away from car analogies. But this building here, in my opinion, it's a little bit overglazed for the size of the building because it is quite a small building. But the important thing is to have windows for daylighting and views, not to gain energy. So if you come out of the passive solar background, as it were, there's a lot of passive solar books out there. I grew up in the United States in Passive Solar Central. Those buildings are designed to capture as much energy as possible. And then generally they tend to leak all that heat out very quickly. Instead, passive house is designed to let the energy out or let the heat in very slowly. So you need less glass to do that. So generally, if you put the glass in for views and daylight, and that's it, then you end up with enough glass in the building. Actually, I usually end up trying to reduce it even. All right, so the next thing is when you're designing a passive house, you need to leave space for ducting and equipment. Now this is a mechanical ventilation with heat recovery unit. So this is, oh, here you can see it here in the closet in this drawing on the left, which is thanks to Archetype. So this is a Zender MVHR. There's a number of other brands available. There's Stiebel Eltron, there's Brink, lots of different brands that are all certified units. So they're very good quality, and you know their quality because they've been tested by a third party. So the MVHR sits there and it takes in external air from the outside, fresh air in, exchanges the heat with the exhaust air coming out of the building and exhausts the air out. So that can be used to recover both heat in the winter and cool in the summer. So in a very hot climate, like Darwin, for example, you would use an energy recovery ventilator like this, and it would actually recover cool. So when you air condition the space inside, the cold air going out would pre-cool the incoming air and help condense out the moisture of the air coming in. You'd still need to have some air conditioning inside, obviously, because you're still leaking heat into the building. But MVHRs are useful for both retaining heating and cooling in the building. So effectively, if the inside of the building is hotter or colder than the outside temperature, they're useful. And the important thing I wanted to point out here is that in this particular building, they chose to use a posi strut midfloor, which is this web here, to allow them to run this ducting everywhere. These ducts are around 90 millimeters in diameter, and they're semi-rigid ducts, so they don't collapse flat like the cheap ducting you see. But they need a space to run. So one of the things we often find is if we come into a retrofitting passive house into a design, a client decided they want a passive house, but they've already got drawings, is we end up trying to find space either underneath the ceiling or in a mid-floor, ideally, to put in ducting, and that's quite an issue if you haven't designed it. This building was designed to be a passive house initially, so that's the reason they put a posi strut mid-floor in. So it's important that if you're designing a passive house that you leave space for the ducting and equipment. The MVHR can go in the garage or the basement, although it's much easier to keep it inside the house itself. So these are also fairly quiet, but they do make about as much noise as a fridge, maybe a tiny bit more. So they're best if they're in a closet, not in the bedroom wall as well. Continuity is key. So when we're doing a passive house, if you noticed on that principles, there was a slide, there was talk about thermal bridging. So a lot of folks who do passive house design really focus on thermal bridging. So I agree, it's much easier for designing a passive house to take the steel out and use timber. So if I'm certifying a passive house, one of the first questions I ask when they ask for a cost, for how much it costs to certify, is do you have any steel in the building? Because if the steel in the building always causes headaches with trying to pull it inside the thermal insulation layer or do something else with it, or how it attaches to the slab, or does it go through the walls? It's always causing headaches. But timber is much easier, whether it's just standard laminated timber or something fancy. The thermal bridge caused by timber is very small because timber itself is only 3 times more thermally conductive than fiberglass insulation, whereas steel is on the order of, well, it's more than 100 times as thermally conductive as the insulation. So it's just it's more than an order of magnitude difference. So this is a very well designed slab edge detail. As part of our company outreach process, we have a book we've done, we'll talk about in a few minutes, and we also do a newsletter every month. And one of the things I did about 8 or 9 months ago, I wrote an article for our newsletter on thermal control layers and making sure that they're in the right place and they do the right things. And we'll talk more about that in just a moment. But that I was asked if they could publish that article in Equilibrium magazine, which is the magazine put out by the AIRAH, the Air Conditioning and Refrigeration Organization in Australia. So it's called Equilibrium magazine. They published this article, which unfortunately is no longer free, but I've got the same article on my website if you want to see it. And it's this whole idea of a control layer hack. So when you're building an assembly as an architect or designer, you should be thinking about the control layers in the assembly. And there's 4 control layers in kind of decreasing order of importance. And this is going to be really weird to hear in a passive house conversation. But the most important thing is to keep the rain out. The most important control layer is the water control layer, the one all the way on the left here, the rain control layer. So once you've got the rain kept out of the building, we can do everything else. Where the building leaks water, you're screwed. There's just nothing you can do. So this particular detail here has 2 water control layers, a rain controller on the outside with a vented cladding, and then a weather resistant barrier or a water resistant barrier beneath it in purple, right? So those are the water control layers. And then the next most important control layer is, well, it's either air control layer or vapor control, I'm not sure which, but it's one of those 2. Typically it's an air control layer, it's the most important. So the air control layer is the next most important, and that's that red line there. In this case, a concrete slab is certainly an air control layer because concrete's airtight once it's cured, once it's cracks. And then there's a Intello on the inside, like in the picture we saw earlier, that's I think the air control layer. And those same 2 layers are also vapor control layers. right? This detail is done for a heating dominated climate, so the air and vapor control layers are on the inside. Yeah, there. And then finally, the least important control layer is the thermal control layer, right? The insulation here, which lines up through this timber with the slab edge insulation, and then insulation under the slab. I've got a minute, I'll tell you the funny story. So I was in Wollongong at the Building Science Conference, which is run by ARH. And I literally got, well, I didn't quite get mugged, but I nearly got mugged. It felt like I was getting mugged after the conference. So I spoke up and said, hey, this is how you do details in New Zealand. And I described this detail right here. And literally three civil engineers like surrounded me after that thing, like we're time for coffee time, and just literally surrounded me like, you can't do that. Nobody would build a slab like that anywhere in the world. You're totally going to get termites. It's going to fall down. Like, you can't do that. And I'm like, here's some photos of a building in Wellington where we have earthquakes a lot, by the way, and it's not a problem. And you're like, you can't, how does that work? It's like a bridge on its side. You put the foam down, you put concrete on top. It's got a 300 kilopascal. It's not a problem. I'm like, you got termites. They do this in America too. They've got lots of termites. Trust me, they got termites in America. And the thing they do in America, which obviously you need to do in Australia, but not in New Zealand, is they basically seal a bit of stainless steel mesh across the top of this foam insulation and leave it flaring out. And then they mastic it to the concrete so the termites can't get around it. So in New Zealand, we don't do that. We can just run the foam up and put timber right across the top because we don't have termites, thankfully. Please don't export termites to New Zealand. I really like our non-termite construction. So it was crazy because they were like totally in my face, and I showed them some pictures, and they like thought about it for a few seconds, and they're like, you're right, you could do that.
I love that. I love that.
Yeah, I'll try to speak a little slower. Sorry, I get terribly excited.
No, it's awesome. It's awesome to see.
Yeah. It was. I've never been to a technical conference where I literally felt threatened. Like, I mean, these guys weren't huge or anything. Yeah. Well, one could be a rugby player, I suppose, but yeah, I mean, I felt, anyways. But it was good fun. I went off and had my coffee afterwards. But so the important thing for controllers, whether they're air control, water control, thermal, or vapor, is just make sure they're continuous. So when you have that section of your building, you should be able to trace the water control layer from the top of the roof down to the ground, and you should have a gutter somewhere. And if you trace the air control layer around your building, it should be continuous. It shouldn't stop because you've got gypsum board up the wall, and you've got to pretend gypsum board's a good air control layer, so gypsum board in the wall is fine. And then the ceiling starts a half meter away above it somewhere maybe, and the air controller is not continuous. When you do that in New Zealand at least, and oftentimes in Australia as well, you get damp interior moist air up in the ceiling space, and then you get a cool night sky, and then it rains inside your building on sunny days. I've got dozens of schools in New Zealand where it literally drips on students' desks in the winter on sunny days. It doesn't drip on cloudy days, only on sunny days. But the poor kids, they've got a brand new school, they're all excited, and the poor principal doesn't realize he's got a school that's got water dripping out of his roof on sunny days. Yeah, and a simple air controller will stop that. You can use plywood, you don't have to use membranes. All right. Okay, so in order to promote Passive House in New Zealand, I've put together a book called Passive House for New Zealand, which you're welcome to download from this website. It does work, I just checked it. But for some reason, if this website, warmhealthyhomes.co.nz, is blocked, you can just go to sustainableengineering.co.nz, and there's a library button, and you can click that.
I've just actually shared the handout of this. Yeah, I've just shared it on the right, so I can see people are downloading it like crazy. Yeah.
Okay, cool. That's great. So enjoy the book. It's we put it together as a bit of a labor of love, and what's in there is 24 or 26 certified pass. At the time I published the book, was every certified passive house in New Zealand, and you'll be happy to hear that the Australian Passive House Association likes the book, and they felt a bit competitive, so they're going to be producing a book similar to this for Australia very shortly. So I've given them permission to use all the text they want to out of it, but they're going to rewrite it, of course, for Australia. Yep. And there's a lot of certified passive house examples in Australia. There's even, like I said, you've got bigger passive houses than we do. I'll show you a picture in just a sec. So I do want to take a moment. We talked about a simple compact form. We talked about making sure controllers are continuous. This building here looks very complicated to the untrained observer. So if you look at this facade of the building, it's very deep. So you can see these shadows coming across. So you know that this wall actually goes into the building. But this building's actually flat across the front. So if you look at the windows, they're all in the same plane, and the building is flat across the front, and only the rain screen comes out, provides any depth or form to the building. Otherwise, it would look very boring. So this passhouse designer is quite experienced. He worked in the UK for a while before immigrating to New Zealand. Sorry, coming back to New Zealand. He's Kiwi. And because he knew that he wanted a simple form for his client so he could give him a good, efficient building, as well as have that real depth and context to the building, he took and built a very beautiful timber screen that's not, so this is just a rain screen. It's just a rain screen is 1.2 meters deep in some places and 50 millimeters deep, or 45 millimeters deep in other places. And it made the building very architectural while keeping it very simple and inexpensive to build. So hopefully by looking through some of the case studies in this book, and eventually when the one that comes out from Australia, it'll give you a bit more feel for how things can work. So the next slide is to encourage you to do that. So I encourage you to connect with the Australian Passhouse Association at this website. And for your next project, know how to perform before you build it, model it. Right? If you go to the Australian Passhouse Association website, you can sign up and they'll let you download this very nice book, which talks about Monash Hall, which is the largest certified passhouse building, to my knowledge, in the Southern Hemisphere. It's a student dormitory in Australia. And unfortunately, I couldn't get permission to show their photos, so I have to show this.
I've just shared that as well. I stole it from their website. But they're actually, I think they have been giving some talks around this. So it's worthwhile actually going to the Passive House website and just seeing what kind of talks that they're giving around this building. I think you've actually attended. I know I have attended some, but it's fascinating.
Yeah, there's some really brilliant passhouse designers in Australia. You know, when I design passhouse buildings, I have to get them certified somewhere else. So I typically get them certified in Australia, and the same thing for me when the certifiers in Australia design their buildings, I oftentimes will certify their buildings. So that's how we end up doing that. So yeah, so if you sign up, I think you said they were going to do a presentation on Monash Hall, which is this particular building.
I have a feeling it's today. Not even at this time. I don't know. Yeah, I would just suggest people just check out passivehouseaustralia.org. But the details should be there. Someone watching here may know, but yeah.
All right.
Yeah.
So now we've got time for questions.
Fantastic. Well, we've got a few questions. Oh, it is. It's this evening. It's by Architects Declare. Thank you, Lauren. Thank you. I knew I'd seen it. I saw it on Facebook. That's brilliant. So if you, just go to Architects Declare. They've got a Facebook page.
Yeah. So that building is all cross-laminated timber, the entire building, except the bottom floor. And so it's all CLT and timber. It's just gorgeous. And they've also done some really good slides on the cost premium they used. And it's interesting because if you look at that facade, the facade is hugely architectural. It makes the building look incredible. But they pretended that facade was all a passive house cost. Nothing to do with the rest of the building. It was purely caused by passive house. So interesting. But yeah, they've done some great presentations.
Okay, some questions. Hamish asked, what does the PP in PHPP mean?
So it stands for Passive House Planning Package.
Oh, right, okay.
So planning package. So it's effectively a very complicated Excel spreadsheet where you put basically build the building in a spreadsheet and use performance.
What's your opinion on underslab insulation?
Either underslab insulation or timber floor on piles is the two approaches that work best. So you can use insulation on top of the concrete slab as well. But that's interesting. That's my opinion. It's high embodied carbon, putting insulation on, having a concrete slab and insulation underneath it. Certainly the best approach, in my opinion, for the long term is going to be a timber frame floor and piles with insulation. But if you've got a site where you've got height limitations, like a single family home in a dense neighborhood, you're going to have to put the building into the ground. And in that case, I think that having insulation underneath the concrete slab is the best way to go. The only time that changes if you're going to have brick or stone cladding that's quite heavy, then we'll oftentimes put the insulation above the concrete slab underneath the floor. That means you don't get any thermal mass benefit, but honestly, if you're keeping the house at constant temperature, there's not much benefit from thermal mass.
Interesting. Does Passive House allow for passive ventilation strategies?
Yes. So I haven't certified a single building in New Zealand that's using air conditioning during the certification. They all assume that they're going to have natural ventilation in the summer for cooling the building. and that works really well. The issue is that you have to account for it. So if you're over the overheating limit, if your building overheats too much, even with natural ventilation, then you've got to provide air conditioning.
Okay, questions coming thick and fast. Is Passive House skewed to consider heating over cooling?
Yes,
it is.
Yeah, that's totally true. Yeah, I mean, they've hugely adjusted the code, so it now very accurately predicts overheating. I shouldn't say that. In my experience, it accurately predicts overheating. So we've had some buildings overheat in Christchurch in the summer, this past summer. And if you look at the model for the building and the way they're running the building, they're not naturally ventilating the building because they've got noisy streets next to their house. The overheating prediction is quite on the.
So, like, let's say, for instance, you're doing a passive house in far north Queensland, where it's typically very humid and hot around.
That's right.
Is Passive House a good solution?
Yes, because what it does is it predicts the interior environment, right? So what that would encourage you to do is to use less glass, to have the windows facing south,
right?
To put in air conditioning, that sort of thing. So it responds to the climate, just like I showed the cabin moving across the climate zones in Australia. So it's tracking the reduction of heating loads. It also shows the increase in cooling loads as you move into those climates. It also does a reasonably good job of predicting the interior humidity levels. So if you're in far north, you would say that not only do you need air conditioning, but one of the problems with low energy buildings, and it's true for any low energy building, passive house or not, when you reduce the cooling load by making good shading on that building, you have less air conditioning required. Because you have less air conditioning, you have less drying of the air. So now you need not only an air conditioner, you also need a dehumidifier or an air conditioner that can dehumidify and then reheat. And that's been found with passive houses and other low energy buildings, that as you get the loads down for cooling, that's great for energy, but now you need to be careful with moisture as well. And that's taken into account quite accurately.
Quite a juggling act. Daniel just said, is timber the preferred material for windows? And I suppose that we could extend that to the frames and everything within a house.
Yeah, so timber is definitely a preferred material for the whole structure of the building. And timber is certainly the most beautiful material and the longest lasting for window frames. But if you're doing if you're doing a social housing project anywhere else besides New Zealand in the world, you're going to use UPVC for the windows. And oftentimes you have UPVC windows if they're imported from Europe, for example, the frames. So we have UPVC windows we manufacture here in New Zealand, and all the UPVC core is actually a different color because that's all post-consumer UPVC that's been recycled. And only the outside skin of that window will be virgin UPVC. Also, UPVC is not appropriate for Central Australia. It's not an okay material to use. You need to use aluminium clad UPVC or aluminium clad timber for Central Australia. It's not an appropriate climate.
Just had a few people asking if we can go through the questions that you wrote for the presentation.
Oh yeah, sure. That'd be great. Can you bring it up? Or
I'm just trying to bring it up here. I thought I had the document open. Okay, here we go. So why should you have an energy model, the PHPP model, done early in the design phase?
Should I give the answer? I think you should model it because you should know how the building's going to perform before you build it, right? So if early in the design phase you find out that the building you've done actually requires no heating because it's got a wall of west-facing glass and no shading, but you want that wall of glass facing west. So I can just pick a different glass that has a very low solar admittance number and show that all of a sudden I need a little bit of heating, but it's not a freaking oven in the summer. Or I can put solar shades out to stop that. So by doing that energy model early in design, you can give your clients what they want without breaking the budget.
Passive house certification guarantees something thermal comfort.
Sorry, I skipped that one in the top. So passive house, yeah, that's my bad, sorry. So passive house certification is designed, I just said it was biased towards heating loads. So it's biased towards winter thermal comfort. So the passive house standard effectively guarantees winter thermal comfort. Like you have to have the windows so you can't be cold next to the windows. So literally on the coldest day of the year, you can be naked next to the glass windows and you still feel warm, right? Because the window surface temperature on the inside is actually warm enough. But it allows overheating in the summer. So therefore you don't have a guarantee of thermal comfort in the summer because it says you can overheat a little bit in order to allow for natural ventilation and not require air conditioning everywhere. So that was the balance they chose in passive houses, to require winter thermal comfort, but allow in the summer some discomfort.
What is the performance gap?
So we did look at that. So the performance gap is if you do an energy model with many standards, like Energy Plus, or it doesn't really matter what software package you use, but I won't get sued by Energy Plus for saying that. When the energy consumption you predict for the building is oftentimes very different than what's actually experienced in the field. And that's true. I can say it about Green Star in New Zealand because they won't sue me either. There's this performance gap. So part of that's caused because all the engineers lie when they build the energy model. We all lie the same way because it's legally allowed by the building codes in New Zealand and Australia. But it means that the prediction model is totally bogus and doesn't give you the right results. Asphalt certification is designed by physicists, not politicians. So we're not allowed to lie. And the model has to predict what the building's going to do at the end. So if you do an energy model per the building code in Australia and New Zealand, you can literally ignore the fact that between the top of the ceiling in your office building and the floor above, you've got a steel beam with no insulation and it's solid concrete. You can pretend that doesn't exist. You can put in R value of infinity for that. And that's what we do because that's what we're paid to do as engineers, right? We ignore that because it's literally in the building code says you don't have to count that. Now, in pass files, it says you got to actually calculate that thermal bridge and account for it. So the results are very different. There's no performance gap in pass file certification because somebody's checking to make sure you didn't cheat and they're looking at the physics. Whereas the building code, they're just concerned about code compliance. Is this building legally allowed to be built or not legally allowed?
What are the 4 control layers in any building?
I did good on that one. Water, air, vapor, thermal.
Okay. What is a building's form factor?
It's the surface area of the building divided by the interior floor area, usable floor area. So if we look at the cabin we looked at, it has a very good form factor because it's very compact. We looked at the straw bale building as a very compact, squarish kind of form. A sphere would be the perfect form versus a long, stretched out building with pods connected by glass hallways, which has a poor form factor.
And we see a lot of those. Well, I do.
Yeah.
You see on the structural drawings that the timber lintels over the larger openings have been replaced with steel. Is that a slide in here?
Yeah, sorry, that slide got deleted. I decided I didn't want to get that technical. So if we click back in the slides, it's all right. Yeah, we deleted that slide.
Oh, no, that's okay. That's okay.
So go ahead and go to the question.
So on this,
no, I understand. So it's about continuity of control layers. Is this one right here? So we talked about the fact that you should avoid steel in structures where possible. So if you designed a building and you've done a good job as an architect and you put timber lintels over all the windows and you get the buildings back, you get the structural drawings, which are of course done after your consent. Anyways, it's another story. And you see that unlike the timber lintels you specified in your plans, the structural engineers put steel in. You should be pissed because now you're gonna have cold strips over those windows that are letting heat out or heat in if it's in Darwin, right? Now you've got these hot spots over your window where all the heat's coming in the building because that's steel. Whereas if you had a timber lintel, you wouldn't have that problem. Because again, we talked about, timber through the thermal controller is not really very much of a problem. Steel is a huge problem because it's an order of magnitude more heat transfer.
So no one should be using steel, aluminium, or anything. They should just simply be using loads and loads of sustainable timber.
Ideally, you use timber. If you do use steel, we just pull it to the inside. So if you think of the cabin, the Adobe cabin we just looked at a little while earlier, if you look at the beautiful interior photo, I don't know if you can click back to that if you've got control of the slides, but that cabin has got 3 steel portals, but they're actually inside the building completely. They're inside the timber layers. You can just see it in the top right of that photo. There's a steel portal there. So it's the next one. There you go. So if you look from the inside of the building, you can see a portal right up in the top right before you hit the drawing. So those steel portals are completely inside the building, so they don't cause any thermal bridging because they're inside the insulation. That also means that steel is very warm and it's never going to rust because it's just never going to get cold and have any moisture on it. Whereas if you put it through the thermal envelope, it's going to pull the heat from the building to outside, which means the inside steel might have a problem with moisture.
And
just like aluminium window frame.
Yeah, and then also had the question here: what size windows are permitted in passive house?
Any.
I like that. Easy.
Yeah. So yeah, we looked at the building, the school in Australia, which has effectively got walls of glass in it, right? That probably should be the last thing we look at, something from Australia. Here we go. Look at all that glass.
Jason, can I?
And they've done glazed office buildings with nearly 100% glass in Europe with quadruple pane glass.
Wow.
That was incredibly expensive. It was crazy amount of money. It was a bank. They could pour as much money as they wanted to in that building. So
Yeah.
Jason, do you have any advice for designers around establishing costs when they're having the conversation with their clients? It's always going to come around cost. How would you suggest designers go about establishing cost premiums and what have you?
It's best to just get a quantity survey and put together the plans and look at the costs. So oftentimes you'll find that you're up-speccing the windows, like you might be going from a standard aluminum frame window to a timber frame window. So you might think that is a considerable cost premium if you're going from a standard double glazed aluminum window to a nice double glazed timber window. That's a huge cost premium, right? But if you're already going to get nice timber double glazed windows already, you might just be buying better glass. So it really depends on where you're coming from and going to. So a lot of times when people look at passive house costs, they're like, well, I've got this really nice upmarket passive house. And all the passive house, if I take out all the passive house stuff, so if I take out the really good windows that make the building quiet and work well thermally and put in the cheapest double glazing I can find, aluminum frames. And if I take out the ventilation system and then don't put one in, just tell them they got to open the windows when it gets stuffy at night. And I take the extra insulation out of the roof and the walls, and I don't insulate the slab, then you might take 8% out of the building. But would you have built that building in the first place if it's a custom house? I mean, you would have built that way if you're doing social housing, really cheap social housing. But yeah, so the cost difference, typical numbers you see are like 8% if they do a fair study that you could pull out of a building that's a passive house if you just put cheap shit in it. But if you're building a medium to upmarket sort of residential home, oftentimes the up cost for passive house, if you start with that in mind at the beginning, is oftentimes not very much. You know, if you were going to actually put in good windows to start with. If you're going to put in cheap crap, then yeah, of course it's a lot.
I've just shared a quick poll. If anyone wants to get some timber sample or receive some links, just let me know about some of our products. We'll go over a couple more questions before we.
I mean, there's a lot of people still staying on, so we've got a little bit of time.
Yeah.
Yeah, I've got time at this.
Sorry. Yeah. Is there any data? Alex just asked, is there any data on the additional cost and possibility in additional embodied energy of, say, a 3-bedroom house designed to passive house standard versus BAU?
Build it business as usual, I think is what BAU means. So yeah, so the first of all, the embodied carbon increase in a passive house versus a typical house is very, very small. So I've done a study on that. And if you go to my website and just type LCA for life cycle analysis, there's a whole presentation, including an hour-long webinar I did for the International Passive House Association. So I presented that paper in China before this whole COVID thing. And so effectively, there's a very small actually sometimes even the decrease in embodied carbon. It depends if you count the biogenic carbon in the timber. So oftentimes you have a timber frame passive house and you add additional insulation, making the walls thicker. So you're adding additional timber as well. And because fiberglass insulation has very low embodied energy, you're adding more timber, which sucks up CO2. So you actually might be negative, which is quite funny to think about. And oftentimes you're switching from aluminum frames to timber frames when you go to a passive house. So, but if you have a concrete slab, the concrete slab doesn't get any thicker. You just add more insulation underneath. So the additional embodied carbon in a passive house versus a business as usual house is very small and sometimes negative, although that sounds weird. So I didn't believe it myself, which is why I went through that whole process. Now, more importantly is the operational carbon of that building is because your heating cost is cut by 90%. And oftentimes the overall energy use of the building, because you're also looking at things like efficient appliances and lights, you might cut the overall energy use of the building by 70%. And that's carbon savings every single year. So the carbon savings from operational carbon savings, switching from a business as usual building to a passive house, are significant. And once you've done that, then it makes sense to start looking at the building, and you want to stuff as much timber you can in, and you want to stay away from steel and concrete. But that's pretty much what it comes down to. So, and there is good data on that, and there's also good data on costs. So Andy, I'm sorry, I forgot his last name, did a great presentation on, he did a cost comparison of a passive house. He actually designed a house to not be a passive house. Thank you. Andy Marlowe, that's right. Excellent job. So yeah, he's like a friend of mine and stuff too. Anyways, I swear, he's a nice guy. So he did a non-passive house and actually had talk to a builder. He was going to build it, and then the client's like, no, stop! I want a passive house now. So redo all the drawings. I want a passive house. I'll pay the money. Just do it. So Andy redid the whole house as a passive house. Gave the drawings back to the same builder, and the cost stayed the same.
Guys, I signed up to Jason's email. He sends an email once a month with like just really useful stuff, and I found it really good. So if you want to hear from him, I've just shared a thing on the side. He just shares an email once a month with case studies and useful info and just stuff happening around Passive House. Back to questions for those of you still on board. Miriam, I just wanted to know, is there ever a need for thermal mass when you're targeting Passive House certification, especially in Perth?
So thermal mass generally is not terribly useful in a high performance building. So thermal mass is most useful in a passive solar house where it's 10 C at night and 30 C in the middle of the day. So on the average is 20 C, right? So what happens is during the day when it's 30 C in the house, the heat gets put into the slab. And at night when it's 10 C in the house, the heat comes out of the slab. So you're making that slab act like a battery and move heat from day to night. But if you kept the house at 20 C all day and all night, then the only way that energy can get into and out of the slab is by direct illumination by the sun. So it's not as effective. So in the passive house planning package, it does take into account the thermal mass. So you put that in. So in Perth, you might see a 5 or 6% benefit in lowered heating demand and in lowered cooling demand by having thermal mass in the building, but it's a relatively small effect. So when I do initial designs, I actually don't ever look at the thermal mass in the building. I put a number in that's representative, and I'll tighten it up later on when I'm doing certification, but it doesn't tend to have a huge impact. Even going from a very lightweight structure like a timber floor on piles, which has no mass in the floor and it's just got gypsum board in the walls, taking that building and compare it to an all concrete building with concrete mid floors and concrete roofs and everything, the difference in oftentimes is only about 10%. Oh, wow. So it's not as effective as you might think in a high performance.
Christina just asked a very interesting question. What is your opinion on underfloor heating versus gas ducted?
I would never put combustion device in a building, so gas ducted's dumb.
Oh, no.
Period. So by that, I think they mean using hot air to move energy around the building. So I certainly would use an air source heat pump because it's the least expensive. I put it in a lot of our lower cost buildings. Underfloor heating is fine in a passive house. There's no reason not to use it, but you do have to realize that the heating load is so low that in the winter when you're walking around barefoot in your exposed concrete slab passive house, that the slab will still feel cold because the slab's at like 23 degrees centigrade and the air's at 22 degrees centigrade because that's all you need to heat the house. So the slab's still going to feel cold because it's much colder than your feet, right? So, but it is nice. I mean, if you run underfloor heating, it does allow you to store, let's say, PV panel energy using a heat pump to push hot water into your floor. So it allows you to just take that sunlight and store it for that night in the floor, as it were. So that's not a problem. So it's good. It's just more expensive than using an air source heat pump.
There was a couple of questions here from Lauren. I think we confirmed this. Yeah, no, we covered that. Is there value in reverse brick veneer?
I'm afraid I don't know what reverse brick veneer is. Sorry.
That's thermal mass, really, isn't it? It's the approach to things.
Oh, do you mean brick veneer inside of the house? Yeah. So if you put if you have the walls heavyweight, like double gypsum board is a common thing to do in the United States. You just put 2 layers of gypsum board on the walls, or do brick veneer on the inside. That adds to your thermal mass and it has the same kind of small effect. So if you did a few walls in brick veneer on the inside, then they might add a few percentage reduction in the heating load. for cooling load.
Can I just butt in with a question? And as a novice, just how far does Passive House consider the embodied energy or the carbon capture around the selection of the materials? You know, what type of cladding should I have, and you know what sort of material selection in terms of the amount of carbon that's in the materials or not? Does it?
Yeah. So Passive House standard is materials agnostic.
Okay.
So you can make the whole thing out of dead baby kittens and mercury as far as the standard.
What was that? Dead baby kittens? Is that what you just said?
Dead baby kittens and mercury. So no, seriously, it doesn't you can laugh, I'm not in marketing, right? I'm an engineer. So it doesn't look at the materials used in the envelope in terms of embodied carbon. Now I'm working on a plugin. There's actually already called a pH ribbon, which is a plugin that calculates embodied carbon using the Passive House planning package, but that's an additional thing. Now, because embodied carbon tends to go along with material density, in other words, low density materials tend to have low embodied carbon, like wood is lower density than steel. So wood has a much lower embodied carbon than steel, obviously. And steel is much more thermally conductive. So you tend to find that passive houses, because they've looked at thermally efficient materials like timber and fiberglass and insulation, they tend to be lower embodied carbon than a similar building built otherwise. But this came to a head when I was in China at the International Passive House Conference in China. We looked out the window of our hotel. We could literally see a forest of concrete core buildings going up. And every one of those is going to be a certified Passive House, right? Now, that's great. They're going to use 10% or less of coal-fired electricity in China, right? Which is brilliant. They're going to be much lower operational carbon. But I'm looking out there with my friend Monty from Canada, and he's like, we've got to go to CLT. Like, we've only got 10 years left, right? 15 years left to get this stuff sorted. We can't have all our passive houses have concrete cores. We need to switch to timber. And so that conference and the next conference that's planned for passive house is really focusing on how we also make sure we're looking at low embodied carbon materials, but it's not in the standard, and it likely won't ever be, because the standard is physics-based and it looks at that operational energy. Now, you might also do embodied carbon calculations, and that's certainly something I want to do in our practice. So right now, every building we look at, we produce a passive house planning package model, and we show the client how they can get a better building for different steps in their performance. So if they want the certified passive house, meaning this kind of windows and this kind of envelope. If they want the low energy building, which uses twice as much energy as a passive house, they can use double glazed windows in Queenstown, right? But I also want to show the embodied carbon at the same time for those assemblies.
It makes sense to bridge. It makes sense to bridge the two and have that hybrid approach where
there is, and I've done a lot of work with LCA Quick, which does embodied carbon calculations for New Zealand, to do that, but it still takes over a day and a half to do a single family home embodied carbon calculations, and it needs to be very quick. So when I take a couple hours to do a passive house planning package model, I also get the embodied carbon calculations, and that's the kind of tool we're working to build here.
Wow, I could go on for hours. Let's take
more, Joe. Listening to Jason, you just want to know more, don't you? So we might have to have him back at some point in time in the future.
But basically, the summary from that is, if you want to be truly help us with net zero in the next 10 years, do your building passive house standard and make sure everything is timber.
It's funny because Paul Ha advocates that it's far more impactful to consider for the coming years in terms of the environment globally, to consider the embodied energy or the amount of energy that's going to the houses.
Mm.
Yeah, I would disagree that it's not important until you get the energy consumption down. So when you talk about a passive house, if you look at over the next 20 or 30 years, for a passive house energy consumption, the operational carbon is about half the energy consumption. But if you look at a standard building that's being conditioned to the same interior temperature, the embodied carbon is a tiny fraction, it's like 5 or 10%, versus the operational carbon over the next 20 years. So first, in my opinion, you've got to step to a high performance building like passive house. We can call it something else if you want, if you don't like that name. We've got to step to that high performance building and then make it out of timber, right? So it's the same thing. We both want to get to the same result, I think. But it's important, to me, it's important first to consider operational energy and then embodied carbon, and not, we only make them out of timber and let's not worry about how much energy.
Probably the most important thing is the whole retrofitting thing, which we won't get into. I'm dying to ask you about the whole retrofitting thing.
Yeah.
But that's probably
we could talk about it for an hour. It's a really interesting
topic.
That's a whole other discussion.
Yeah.
Cool. We should probably stop off there. Thank you everyone for coming. Yeah, please send in your questions. And thank you so much to Jason for presenting today. It was so interesting, Jason. Wonderful. Yeah. Yeah.
Thank you very
I
much.
hope to see you guys next time. We do have another webinar in the next few weeks, but we will be announcing that start of July. So hold on to your hats. Cool.
Thanks, Jason.
Thanks. Cheers.
Thank you, Ron.
All right. Cheers,
Bye-bye.
Joe. Cheers, Steve.